and probably semiconductor, and which all of them probably come up from the sand particle. So that's why I said, let the sand imagine how much dark matter a galaxy has. So these days, not just human that can think, but the sand itself can also think. Let us move to the next. Okay, so the content of the talk today is about, self-introduction, just a brief self-introduction, and also I will cover a little bit about the dark matter, which had already been covered by my senior Darren. And I will also cover about the AI, the artificial intelligence. And after that, I will be talking about seeing the dark matter in the galaxy with the AI, which is my current project, which is not going very well. But I will try to make it simple as much as I can to make everyone understand. And I also give a brief introduction about the cosmological simulation, which is very, very introduction level. And finally, I will summarize the talk. So self-introduction, I think everyone might know me by my name because I used to be a physics student in Royal University Phnom Penh of Phnom Penh. So my name is An Bunkhuoch, and below is my email, and I am currently the 4th semester graduate student at Seoul National University, which I'm doing the research related to the dark matter in the galaxy using the AI. Sorry, so technically this is me and this is my team. So let us talk about the dark matter. So I think everyone knows what dark matter is right now because of the previous presentation. And I just give a short talk about the dark matter. So let us go back a little bit further than Fritz Zwicky. We go back to around 1600, which is about Keplerian time. So Kepler obtained the data from Tycho Brahe that is related to the planetary orbit. And then from that, he obtained the Kepler third law, or the other two laws as well. And also he obtained the Kepler third law. And from the Kepler third law, we can obtain this relation itself, which tells us that the velocity is inversely proportional to 1 over the square root of r, which means that the velocity will decrease. The orbital velocity of each of the planet will decrease as you goes out to the outer region of the solar system, which means that Mercury will rotate orbit faster, and then and then Venus, and then Earth, and then Mars, and then Jupiter, Saturn, and so on. So therefore, Neptune is the planet that has the slowest rotation speed in our solar system. So it goes according to this curve right here, which is called the Keplerian curve. So the planet should obey all of these curves itself, okay? Right. So we expect the solar system to have this kind of orbit, this kind of rotation profile, or we call it rotation profile or rotation curve. So the system itself should have this kind of rotation curve, as we have seen in our solar system. So what if Jupiter has a slightly faster, or probably having a speed rather than 10 kilometers per second, but 40 kilometers per second? So if Jupiter has that high velocity, then it's supposed to have, which is 10. So if Jupiter has 40 kilometers per second, it means that Jupiter would have high kinetic energy. With high kinetic energy, it would have enough energy to escape the solar system gravitational pull itself. Therefore, Jupiter will not exist in our solar system because it is rotating very fast. So therefore, in order for Jupiter to remain in orbit, it has to follow the Keplerian curve like this. I think everyone should understand. So same goes for Saturn, Uranus, and Neptune. If all of them moves at a speed faster than they are supposed to be, all of them would just like fly out of the solar system. So, so in order for them to be bound to the solar system, they're supposed to have this amount of speed. But what if they don't want to have this amount of speed? If they want to have like 50 kilometers per second for Jupiter or Saturn, so therefore the sun has to be much more heavier in order to have enough gravitational pull to pull them to be enough and pull them into the gravitational bound of the sun, gravitational well of the sun. So I think everyone should understand now that in order for this system to be a bound system, they have to follow the Keplerian curve itself. So let us go back to around 1930s from Fritz Zwicky, which is quite the same story as that described by Dan, which is a little bit review. So this is a coma cluster, and it is around 100 megaparsec, which is around 300 million light years away from Earth. And I think Fritz Zwicky back then observed around 800 galaxies in this galaxies cluster. So galaxies cluster is a group of galaxies that they are very close together, which the space between them is very close to one another, and the entire cluster itself composed of around 800 galaxies, which is bound into just around million light years across, I suppose. So 1 million light years is closer than the distance from Milky Way to the nearest neighbor, which is Andromeda. So in that small region of space, it hosts so many galaxies. This is what I'm thinking of, if I'm remembering the size of the cluster correctly. So Fritz Zwicky observed all the rotation speed of each of the galaxy in this cluster itself, and it turns out that it rotates each of the galaxy orbit the cluster faster than it is expected. So from the light we observe from each of these galaxies, Fritz Zwicky or we can obtain the estimate mass of the galaxy cluster, because, for example, one solar luminosity corresponding to one solar mass. So if there's like 1 billion or 1 trillion stars in this image, there's supposed to be 1 billion or 1 trillion solar mass in this image as well. So from that mass that we estimate, we can approximately identify or measure the rotation, the estimate rotation speed of each of the galaxy. However, when we observe, the galaxy rotates very fast, which if so, that fast rotation would have picked all of these galaxies from the cluster, and therefore there will be no cluster remaining. So Fritz Zwicky thought that probably there's 100 times more mass than the mass we estimate from the light. Therefore, it seems like there's just only 1% of the total mass that we see in this image, while another 99% of the mass we cannot see in this image. And likely about 90% of those mass is dark matter, while another 9% is just a hot gas around the galaxies. So this is the evidence of the dark matter back then. However, nobody bought that idea. Nobody took that idea seriously because they thought that the observation probably not complete, or maybe some error or some kind of things within the systematic, I think. So therefore, nobody took the idea very seriously, even though Fritz Zwicky came up with the word dark matter at that time. So until around 40 years or 50 years later, Vera Rubin studied the rotation curve around spiral galaxies, and therefore, let me talk about this again. So in a spiral galaxy, as you can see in here, so the dashed line corresponding to the expected rotation curve, which the outer region itself is the Keplerian rotation curve, while the inner region is the solid disk rotation curve, which increase probably linearly with radius, as I can remember, but they're not very solid, so it is quite a variation. However, in the outer region, which all of the mass is thought to be within this red circle, So therefore, the outer region itself are just like planets orbiting the sun. So the inner red circle is analogous to the sun, and the stars in the outer region are thought to be orbiting just like the planets orbiting the sun. Therefore, they would show a Keplerian orbit. However, in the observation itself, it shows that all of those stars doesn't follow the Keplerian orbit. They follows this kind of profile, which seems to be increasing or probably flat in the outer region. So therefore, like I mentioned a while ago, like if Jupiter have a very fast rotation, if its rotation speed is going up to like 50 kilometers per second, it will fly out of the sun gravitational pull, and it will fly out of the solar system. But if you want Jupiter to be having 50 kilometers per second, you need the sun to be more massive in order to pull it back into the system. So therefore, if all of these stars having this high velocity, in order for them to have this high velocity, the galaxy itself has to be very much heavier. Therefore, that much heavier mass is the dark matter itself. I think you understand this part now. So in her 1980 paper, she concluded that the conclusion is inescapable that the non-luminous matter exists beyond the optical galaxy. So not just within this red circle that hosts the matter, but the dark matter itself is extended beyond this red circle. It goes far, far away from beyond the visible galaxy. So for example, for our Milky Way, I think that our dark matter halo probably extend to around 1 million light years away from us, up to halfway through to the Andromeda galaxy, which is 2 million light years away from us. So probably both of our galaxies' halos, dark matter circle, probably colliding already. However, the visible part of the galaxy haven't. So this is the dark matter that is into play, that we are able to see this kind of rotation curve in our observational data. So modern day studies shows that on average or overall, the matter that we experience in our everyday life is just made up of around 5% of the universe, while the majority are something that we don't know, including dark matter and dark energy itself. So it seems like there's 5 times more dark matter than the normal matter that we are experiencing these days. However, why we don't see any of their effect on our planetary orbit if there's more dark matter and dark energy in our universe? So I think I should leave this question for you as homework. You might need to consult your personal assistant, which is probably ChatGPT or something, Gemini, something. So this is a review about the dark matter stuff. So let us move to the next, which is artificial intelligence. So the definition of intelligence, then intelligence is the ability to acquire or apply the knowledge and skill. So there's two part here for the intelligence to happen. One is acquire the knowledge, and the other one is apply the knowledge. So this is how intelligence work, and this is from directly from Google itself. So for example, if you have a 2 or 3 years old kid which haven't experienced seeing cat or dog in their life, so at their first time you show them this is a cat and then this is a dog, so they will try to remember or memorize which one looks like, which one is the cat and which one is the dog, which feature does the cat have, which feature does the dog have, probably the nose or the eyes of both of them, probably very different, probably the ears, or probably how they move or something like that. So the kids will try to memorize and try to distinguish between the two. And this is the stage of the kid trying to acquire the knowledge or trying to obtain the knowledge. And then next time when he see the cat and the dog, he will instantly distinguish this is the cat, this is the cat, and this is the dog. So this is how he applied the knowledge itself. So sometimes the application of the knowledge can be mistake. Probably he would say, oh, this is the dog. However, you can still tell him that, no, it is the cat. So next time he will be a little bit more accurate in distinguishing between the cat and the dog. This is the process of learning. So you are allowed to make mistakes. And then comes the word artificial. So artificial is, the meaning of artificial is made or produced by human being rather than occurring in occurring in nature, especially as a copy of something natural. So you're trying to make an intelligence thing, but it doesn't occur in nature. So it is human made. So therefore, this is the definition of artificial intelligence that I'm came up with. However, ChatGPT was not very happy with this definition, but I still take it for the presentation. So artificial intelligence is a human-made intelligence that mimics the ability to acquire and apply the knowledge. So instead of having a 2 years old or 3 years old kid, you have a processing unit, either CPU, GPU, or any other processing unit that I don't know. And then you program that processing unit to take the data and to process the data in such a way that it is very smart, that it mimics the intelligence of a human. So for example, you input all the cat photos to the CPU and then tell the CPU that these are the cat. And then you also input the dog photo to the CPU and then tell the CPU or tell the artificial brain that this is the cat. Oh, sorry, that these are the dog. So they are the dog and these are the cats. And then this is called the process of training. You train the machine or the artificial brain to recognize which one is the cat and which one is the dog. And then the way the machine recognizes all of these images is by doing some kind of processing, which they try to identify some kind of feature of the cat and the dog. So for example, the cat has some kind of fluffy fur, probably a little bit more fluffy than the dog, or it has probably a wider eyes than the dog, or the pink nose, the color of the nose, or probably it looks quite smaller or somehow larger than the dog or something like that. And then the machine will try to remember all of these features of the cat and all the other features for the dog. For example, they have the tongue that coming outside, and then probably the machine trying to identify that mostly they are the dog. Probably the other pixel correlation that we ourselves human don't really know, because the machine is just picking some relationship between the pixel in the images that we ourselves don't really know what the machine learned. We only know the result. So this is the main part of the machine learning. It is just like a black box, and it is just like magic. So then next time you give the machine, so this process is a training process. And then after the training process, it is just like it behaves, and now it behaves just like a human. So after the training process, after inputting all of these images to the machine, and then the machine tries to remember, then you try to input the other images to the machine to test the machine. And then the machine will just label, oh, this is the cat, oh, this is the dog. And this is a cat, this is a dog. No, this is wrong, this is a cat. But the machine label it is the dog. Same goes for this is the dog, but actually it is a cat. So the machine somehow makes some mistakes. However, the accuracy is quite good. For like 94% of the time, it makes a correct prediction. You can go to this link to see how the code and how the models is coded, and how they input into the machine and how they test the machine. So to summary about the AI model, so the AI or the artificial brain seems to take all of these input, which are the images of the dog and the cat, and then the output from the model is just 0 or 1, which 0 indicates the cat and 1 indicates the image is the dog image. However, you can make some adjustment, like 1 is for the cat and 0 for the dog. It depends on you. So the output like this, which is called the binary classification task. So you just classify the image. Which image is the dog image? Which image is the cat image? So this is just a simple classification between making decision. Probably you can do it like rather than classifying the dog or the cat, you can just like tell the machine to output yes or no or something like that. Depends on you. So these are some tasks for the some example for the classification task itself. So our email, it can automatically classify whether an email is a spam email or just a normal email. So if it is a spam email, it will send that email directly to your spam list. And if it is not, it will just send you directly to your inbox. It is already implemented in the email, in the Gmail, probably. So that's why sometimes you don't receive the email from your friends or from somebody else, which is potentially a scam or something like that. So the AI just directly detect and classify between yes or no, between 0 or 1. And also the credit card fraud activities, also the face recognition, and also some kind of, and also the real and fake news identification. Also, AI can help you to detect is there any abnormalities in the medical imaging. So if the image is not normal, it just classify as 1, and if the image is normal, it just classify as 0. Probably you can make some adjustment. Probably if it is normal, 0, abnormal is 1. It depends on you. The choice is quite dependable. So it is very good at helping the doctor for screening the patient rather than just like spending hours to observe all the images. Also, it helps astronomer to detect which galaxies undergoes a real gravitational lensing rather than just a circular disk or circular ring around the galaxy. Also, it helps astronomer to classify between morphology of galaxies, which indicate the shape or size of the galaxies. For example, this is a interacting galaxies and spiral galaxies and so on and so forth. So the AI can help you to do all of this work very efficiently and very fast. So next part, so all of these are just classification tasks. However, let us move to another task that the AI can perform. So classification task is just the task that AI can decide whether it is to output 0 or 1. However, we can force the AI to output any value, not just 0 and 1. So I think everyone would probably know what is regression, because all of you probably have experience doing it in your physics undergrad study. So one of the simple experiment that I can think of, and I ask ChatGPT to give it to me, which is Ohm's law. So for example, you have a setup which you can set the voltage of a power supply, and then you measure the current. So this is X and this is Y. So you can do the experiment and measure and give the value of the voltage to the setup and then measure the current. As you can see, 1 to 0.1 ampere, 2 volt to 0.2. And then you can make your own estimate of the resistance in here. And it turns out that we know the underlying physics, so which it is easy for us. And then we can obtain the linear regression plot right here, which itself shows the perfect fit, which is because this is just a generated data rather than the experimental data. That's why it shows a very perfect fit. So therefore, not just we're doing linear regression, which is not just for measuring the resistance. However, the point of doing linear regression, we also need to obtain the predictive power for the future experiment. For example, from this linear regression, we get this equation right here, or probably this equation right here. So what if in the future I give the voltage to 10 volt? So what will be the current for this setup? So the current would be, anybody knows? No?
It's going to be one volt.
Yeah, it's going to be 1. So if you give 10 volt of electricity to the setup, it will be 1 current flowing through the ohmmeter, to the ammeter. So this is the predictive power of this linear regression line. However, for this experiment, we do know what is the underlying physics. And what if, for example, we don't know the underlying physical law of an experiment, or if the law itself is very, very complicated that the non-ideal experiment condition cannot be achieved. So therefore, we have to move to the AI, because if there's so many parameters that take into play, we cannot take into account all of those parameters. For this case, we only have 1 parameter, which is the voltage. What if you have 10 parameters? If you have 20 parameters, and then you just want to predict the current from just 2 parameters? So it is time to move to the AI. So for example, the regression task that the machine, that the ChatGPT can think of, that I'm asking it, is the prediction of tomorrow's temperature based on today's temperature, humidity, pressure, wind, and satellite images. So if we all know physics, probably if we know all of these parameters, probably everything or every every properties of air molecules in the room, and we know the physics, we might be able to derive very precisely what tomorrow temperature would be. However, deriving that is quite impossible because every random thing's happening. So it is very hard to derive the exact temperature for tomorrow, or probably even estimating. That's why we use the AI. We take all of these things as an input, and then the AI itself try to recognize the previous data. We take all of these as an input, and then tomorrow's temperature as an output, and then feed it into the machine, and then the machine will learn the connection between the historical record of all of these data, and then we can input all of these input for tomorrow temperature estimate. So we give the machine all of these input data to the machine, and then we tell it that, for example, we tell the machine that the temperature, humidity, pressure, and wind and satellite image of the temperature between 2001 to 2024. And then we tell the tomorrow's temperature from 2001 to 2024. And then the machine would learn from all of these data. And then we use the trained machine to take the input of today's temperature and humidity, pressure, wind to predict tomorrow's temperature. So this is how the AI work, and this is the regression task. And the machine doesn't care about the physics behind all of these data. It just predict out from the historical data, and it finds the pattern between the data itself and make a prediction of tomorrow's temperature. So the AI never learns about the Navier-Stokes equation or something like that. So this is for the case like there are so many input parameters. For example, this case we have like 5 input parameters. There should be x1, x2, x3, x4, and x5, and trying to predict tomorrow's temperature, which is y. Comparing to the previous one, which is the Ohm's law, we have only one x, which is v, and then one y, which is I. So this is the power of the machine learning. Same goes for the fuel consumption of the car. We can take the speed, weight of the car, engine size, and road slope, or any other estimate how much fuel it consumes per kilometers. So the AI never learns about the physics behind this. It never learns the Carnot engine or any other things, or the efficiency of the engine itself. No, it doesn't. But it managed to pick the good relationship between all of them and then make a good prediction. So previous study applies to which is related to astronomy itself, which is related to Hong et al. 2021, that he used these two data for the input feature, which he himself tried to study the large scale dark matter distribution. So the inputs are the number of galaxy, the number density of the galaxy in probably in 3D as far as I remember, and also the peculiar velocity. So I might not talk about that, but just note that all of these are the input to the machine, and then the machine would output these two maps. So this is the predicted map from the AI, and this is also the predicted map from the AI with no peculiar velocity is included. So we don't give this input to the machine. We just give one input to the machine, and then the machine tries to predict the dark matter distribution. So this is the output when we use both of them at the same time. And as you can see, this is the ground truth, which is from the simulation. So it reconstructs the dark matter quite well. And as you can see, there's some kind of filament tree structure and so on. So the machine itself probably knows where are the filaments or something like that. And recently, people use the machine to estimate the stellar mass of any galaxy, how massive it is, how much stars it have, probably. And it works better than the spectral fitting, SED fitting. So it is just like a spectral fitting. Probably a little bit more elaboration is needed, but probably everybody, it is very hard to explain right now. And also, this is for the dark matter this is for the dark matter mass estimate. So the input are the photometric data, the galaxy images in different bands, filter bands, and the structural data, how large the galaxy is, and the kinematic data, how fast the galaxy rotate. And then they use all of these data to input to the model, and then the model predicts the dark matter mass of the galaxy itself. So it seems to follow one-to-one relation. That seems like if the real mass is 10 to minus 1, so the predicted mass is also 10 to minus 1. 10 to the power of 2 is also 10 to the power of 2, with some slight small scatter at around this region. So the predicted power of the AI shows very well performance itself. So let us move to what I'm working with. Probably it takes another 10 minutes. I'm sorry for a long presentation. So this is what I'm working with. So I'm just taking a particular galaxy which has the rotation map and the spread of the velocity map and the stellar mass density map, projected stellar density map. And then I input it into the machine. It is a GPU server named Ultron. And then it tries to output the dark matter distribution around that galaxy. And then I train the machine to find the connection between the input and the output itself. And finally, just hope that it will find the connection between the two. And then finally, the machine will be able to predict where the dark matter are in the galaxy itself. So let us move a little bit back. Where do I obtain all of these data? Velocity map, velocity dispersion map, and stellar mass density map. So traditionally, we pass the light of the galaxy through a slit like this, and then this light goes through the prism or the diffraction grating, and then it breaks down into spectra. And then from all of these spectral feature, probably spectral lines, you can estimate how fast the galaxy is rotating and other properties of the galaxy. However, in the IFU or the integral field unit, you're rather placing a slit in the center like this. You sample the light, you obtain the light from that galaxy by the fiber optic cable, which is the light pipe, just like the water pipe, but this is the light pipe. It transfers the light to the diffraction gratings or the spectrograph, and then break down into spectra. And therefore, every single region in the galaxy itself has spectrum, has spectral data. So this is the image of the galaxy, and this is the wavelength space. So each of the pixel itself has different of the galaxy has different wavelength corresponding to it. I mean, for example, this one pixel in this galaxy, it has one spectra corresponding to it itself. So therefore, from that information-rich spectroscopy, we can obtain some kind of spectral feature. For example, let us look at this image. So this is just for representation only. It is not the real one. For example, this is the absorption line A. So this is at rest. And then if it moves to the right, it is called redshift. And if it moves to the left, it is called blue shift. And therefore, since we know all the spectra in this image, we can obtain the rotation map of this galaxy. So we obtain all the spectra in all the pixels of the galaxy, and then we manage to derive the rotation map of the galaxy. So this is the velocity map. The blue part is approaching to us, and the red part is going away from us. Same goes for the velocity dispersion. It measures how broad the line is. So some stars rotate around the galaxy at this velocity, and some stars rotate around the galaxy at slightly faster velocity, and some stars rotate around the galaxy at slightly slower velocity at this particular pixel. And to obtain the overall spectrum, we just add all the spectra of all the stars, and then we obtain the velocity dispersion, how thick the line is. And for the stellar density profile map, it is very hard, which I'm not trying to talk in here. So for a given galaxy, we can obtain all of these three data, which is velocity spread, how thick the line is, and how much stars in a pixel does that galaxy has. And then I put it into Ultron and then train Ultron to find the connection between the dark matter distribution. And finally, Ultron will learn the connection. But one problem is that how do I know the dark matter distribution from the first place? Because in the real world, we don't know where the dark matter is in the galaxy. So in order to train Ultron, I have to go to the simulation world. So I have to go to the cosmological simulation. So what is cosmological simulation, you ask? So cosmological simulation is just a fake universe itself that is inside the supercomputer. We just put the gas, stars, and dark matter and put all the law of physics that we know of, and then let it run, and then just hope that it will work, and it will represent our universe. So the degree of realism of this universe probably still questionable. However, it shows many studies shows that it is somehow very similar to our universe, which I'm not really sure. There's still something that it is not very similar. So the machine itself, the predictive power of my machine itself is also very dependent on this simulation. If the simulation is wrong, that means the predictive power is also wrong. So within this simulation, you can zoom into all of this structure and find in each individual galaxies, and each individual galaxies, you know, each information of each of the particle in this each individual galaxies, and then you can construct all of these maps. And then you can also construct all of these dark matter map because you input the dark matter itself into the simulation, and then give some condition for the dark matter to not interact with the other matter according to the law of physics of the simulation itself. Therefore, you can train Ultron. So you put all of these features to Ultron, and then Ultron tries to connect the puzzle or trying to connect the pattern. So if you provide this kind of configuration, Ultron should predict this. If you provide this kind of map, Ultron should predict like this, and so on for like another 12K samples. So I feed into Ultron, I train Ultron all of these data, and then Ultron learn from them, and then I use Ultron for prediction for the other sample that haven't trained it. So for this galaxy, this is the performance. So currently I'm testing Ultron. I'm testing the model itself. So I input the velocity map, velocity dispersion map, or the spread of the line, and the stellar surface density, how much stars in a pixel does the galaxy has to Ultron, and then Ultron predict this distribution. So this is the dark matter distribution around this galaxy. And this is the ground truth, which I obtained from the simulation. So this one is obtained from simulation, which is the real one. And this one is from the prediction from Ultron. So if I subtract them both, they are very consistent with 0. So it seems like Ultron performed quite well. And currently I'm still using the simulation data. And I also give some more data to Ultron for the prediction and, for example, this galaxy itself. And you can see Ultron make a very, very good prediction of the dark matter distribution around the galaxy. This happens to be somehow a spiral galaxy and quite offset from the center of the image. How the core itself quite offset from the center of the image. Still, Ultron managed to follow the dark matter distribution. So Ultron is very smart at this point. However, the next step is to apply the model itself to the real data, which is very challenging. So this is the real data, the real galaxies, and then I hope to apply all of these data to Ultron and then make some good prediction from it, which currently it is at the stage of unknown. I will try to update if there's some update in the future. Currently, I'm working very hard on it as well. So note that the predictive power of Ultron itself, of the model itself, depends very much on the simulation that it is trained on, this simulation. If it is trained on a perfect simulation that represents our everyday universe, that means Ultrons give a very good prediction. But if the universe itself in the simulation is really wrong, is a garbage, for example, so Ultron itself would just predict something garbage as well. So the model itself, the performance of the model itself is dependent on the simulation. So this is a summary. Today, everyone learned about the invisible matter that can contribute to the majority of the mass in the galaxy and probably the universe, 5 times more massive than our everyday experience, normal matter. Also, everyone have a small understanding, probably more understanding, experience a small introduction about artificial intelligence. And also, I also gave a brief talk about my project, which is about seeing the dark matter in the galaxy using the AI. Thank you. If there are any questions?
Very good, Bunkhuoch. Yeah. Any question from students?
Yeah, teacher, I have a question again.
Okay. Yeah.
So, thank you, Bunkhuoch, for your interesting topic. And I like to point out about your picture that you name your AI as Ultron, which is, and you use the picture of Ultron that a powerful one. If one day your Ultron become very smart, it can take over the world.
Oh, no. Technically, I think it is the idea of my senior. The name of the GPU server, it's not my. So I just named the model Ultron according to the GPU server.
Yes.
So probably,
So,
I think, as I remember, it is from the vote, which everyone agrees to name the GPU server as Ultron. So that's why the Ultron name is attached to everything, right now.
Yes,
Even my personal Wi-Fi name's also Ultron.
Thank you, Bong. So I have a question with your AI because I think AI is one of the main like techniques that we can use to predict a lot of complexity in physics as well as mathematics. And I
Oh,
heard
yes.
that it also have in biology and chemistry as well. But according to your AI, so what type of AI that you use? Is it from like the one that they already have in open source or the one that you create with your own hardware?
Ah, so technically, the model of the AI, the structure of the AI itself is obtained from the previous study from my professor, which is from Hong et al. So he is the owner of the model. However, I still need to make some adjustment for the data because back then the model used 3D images rather than 2D images. So I have to make slightly small adjustment with the help from ChatGPT. You all know it. So then it takes only
Yes,
2D images. Therefore, it can still give a very good prediction of the dark matter.
I see, Bong. And I also noticed when Bong mentioned about the simulation of the universe that
Okay.
like it's a simulation, but you use that simulation to generate a dark matter position, and then
Yes.
you use Ultron to help identify it. So if example, if you use the fake universe inside a supercomputer, that's one. But your Ultron can predict it correctly with that fake universe. So if
Yes.
example like a time when they come up with the universe that is real that it can generate by supercomputer, so it means that your Ultron is already powerful, right, Bong?
Um, so the definition of this fake universe itself, it depends. I mean, it depends on how real it is. So if the law of physics that we know of today is complete, therefore it is no longer a fake universe anymore. It is more likely the real universe that can represent us, our
Oh, I
universe.
see, Bong.
However, our knowledge of the law of physics probably incomplete. So that's why it is quite safe to call all of them fake universe or cosmological simulation
Oh,
as
I
the
see,
name
Bong. So
suggests.
everything depend on the law of physics, right, Bong?
Yeah, everything probably depends
Oh,
on how we know of the law of physics and the recipe that we take into account the effect from all of these things. Yeah, technically the law of physics. So if
yes, Bong.
our
Thank you, Bong.
understanding of the law of physics is complete, the universe would be very real in this supercomputer, and then Ultron would predict a real thing. But if this is fake, yeah, the prediction from Ultron is still fake. There's a saying for the machine learning or the AI thing. It's just like a garbage in. If you feed garbage to your model, the model would just predict garbage. So please make sure you predict you feed the model a good data or a good, yeah, I think you understand that.
Yes, Bong. Thank you, Bong. So it means that if the Ultron can predict this simulation correctly, it means that it has potential to predict the real one when like if the
Correct.
time comes, they have a technique to get the real information for the universe. So it
Yes,
means that
correct.
your
So
Ultron
it
is
just
already
have
powerful.
potential. Yes, it
I
just
see, Bong.
potential.
Thank you,
It doesn't
Bong.
have the skill. Yeah,
Thank you, Bong.
correct. Thank you.
Very good talk. Yeah. More question, anyone? So it's almost 12 years old.
Sorry for a very long talk.
It was
I didn't
fine,
expect
actually.
it.
Yeah. But you should be tired, I think. Yeah, it's already 12, almost. All right, I actually recorded the talk, yours and also your seniors talk. So I'll share with all the students if they want to listen to it again. I think it's enough for
Thank you.
today's lecture, and thank you so much, Bunkhuoch, and all the talk was interesting actually. Yeah, it's good use of AI in this modern world to predict this kind of thing. I think they should not also tired because it's already the whole day for them. So I think I should end the workshop, the day workshop now, and I hope that students will join this kind of workshop tomorrow again because we have different different talks by different speaker. So once again, thank you so much, Coach and everyone, and see
Thank
you
you.
tomorrow.
Thank you, teacher.
Thank
Goodbye,
you.
teacher.
Goodbye, teacher. Goodbye.
Bye.